Welcome to Oddly Real. I'm Nem Stefanovic. Most of us have an intuition for the dimensions of objects. For example, we know a line segment is one-dimensional, a square is two-dimensional, and a cube is three-dimensional. We also typically associate dimensions of space with possible directions, like moving horizontally in one direction, forward or backward in another dimension, or vertically in a third dimension. These are all very familiar concepts to us. Today, I'm going to talk about some unusual geometric objects that possess dimensionality that is in between these dimensions. For example, there are objects that have 1.6 dimensions and others with 2.7 dimensions. But what does a fractional dimension even mean? How do we even define such a thing? In this episode, we discuss geometric objects with these kinds of dimensional properties called fractals. We have an intuitive understanding of the dimensions of an object based on length, width, and height. However, we can also define the dimension of an object based on how the object scales in size when we make its image bigger or smaller. For example, if we took a line segment of any length and tried to scale up the image by a factor of 2, the line would become twice as long. This is the expected behavior of a one-dimensional line segment. This is true for any scaling factor, not just the number 2, but a factor such as x. Scaling a line by x is equivalent to multiplying the length of the line by x. In another example, let's look at a square. If we scale the square up by a factor x, the scaled image is also a square, and its lengths of the sides of the square would be x times longer. The area of the scaled square would scale up by a factor of x squared. This is the expected behavior of a two-dimensional area. Finally, we look at the example of a cube. In this case, scaling a cube by x in size means the lengths of the edges of the cube will scale by x, but the volume of the cube will scale by x cubed. This defines a three-dimensional volume. In this way, we can say that if we scale an image by a factor x, then if an object scales by x, it is one-dimensional. If an object scales by x squared, it is two-dimensional, or an area. If it scales by x cubed, it is three-dimensional, which means it has volume. This is one way to define the dimensionality of an object. So what exactly is a fractal? A fractal is a geometric object that is made up of pieces that are scaled images of itself. Basically, it means that you can break up a fractal into pieces that look exactly like the original fractal. That probably sounds strange, so it's best to show an example. A very famous example of a fractal is called Sierpinski's Triangle. Start with a triangle. Now use a triangle to take away the middle portion of the original triangle. The removed triangle has a quarter of the total area of the original triangle. Now we're left with 3 identical triangles. Next, take the middle portion of those triangles out in the same way by removing a triangle from each one that is a quarter of its total size. Repeat the process again. In fact, you'll need to do this process over and over an infinitely many number of times. When this happens, in principle, you'll get the famous Sierpinski Triangle. So what's so special about this geometric object? First of all, look at one of the triangles, say the top one. Notice that it's a smaller scaled version of the original large triangle. Notice that the other 2 triangles are also the same smaller scaled versions. In fact, if you drill in further into those triangles, you see even smaller triangles that are also scaled versions of the original. You can see that this image is composed of parts that are just scaled versions of itself. It's a fractal. Although it looks a bit elaborate and unusual, our first thought might be that it's just a regular two-dimensional image, but with successively smaller holes punched into it. In order to understand its dimension, let's step back through how it was constructed. First, we had a triangle, and let's assume it had an area of 1 square units. We started by removing one triangle in the middle. That was 1/4 of its size, which left us with an area of 3/4. Next, we have 3 triangles left that are smaller versions of the original triangle. Now we remove the quarter middle sections from those. That will remove another 3/4 of what area is left. So the total area left now will be 3/4 of the 3/4 we had from the first step. 3/4 times 3/4 equals 0.56. This exact same calculation is done for the remaining area after every step. So the area of the original triangle will change with each step as follows. Going from the beginning, it starts at 1, then goes to 0.75, then 0.56, 0.42, 0.31, and so on. Notice that at each step, the area that we had in the previous step is reduced by a factor of 0.75. Clearly, the calculated area is trending downward after each step approaching 0. If we looked at the calculated area after the 100th step, we get 3.2 times 10 to the power of minus 13, which is very tiny and close to 0. It looks like we're removing all of the area of the triangle. We can imagine this might be okay if we're left with just a wireframe structure of the triangle. Maybe the triangle ends up being composed of line segments. However, it still doesn't seem clear. Let's try a different approach. We can understand the properties of Sierpinski's triangle by taking advantage of its symmetries, since it's composed of scaled copies of itself. For example, the triangle at the top is just a 1/2 scaled image of the original triangle. Why? Because you can see that the length of its sides are 1/2 the length of the sides of the original triangle. The scale factor is x equal to 0.5. Also, the whole triangle is just made up of 3 of these triangles. So the top triangle must account for 1/3 of the entire area of the large triangle. This means that the top triangle equals 1/3 of the total area. Recall that when scaling a geometric object by a factor x, areas will scale by x squared. However, if we try this here, we get 1/3 is equal to x squared, which is equal to 0.5 squared, which is equal to 0.25, which doesn't work. So our assumption that the fractal would scale like a 2-dimensional object is wrong. We'll need to figure out the scaling. The top triangle's area equals the scaling factor x raised to the unknown dimension of the fractal d. We have enough information that we can solve for the fractal dimension d, which is just 1/3 is equal to 0.5 to the power of d. And that gives us that the dimension d is equal to 1.585. The fractal scales like having a dimension of 1.585, whatever that is. It's some kind of a mix between 1 dimension and 2-dimension scaling, almost right in between. There isn't enough area removed to make the image a wireframe, but there's not enough area left to make it fully 2-dimensional. There's another example that involves the removal of squares. We start with a square and then remove a square from the middle of its interior. The removed square is 1/9 of the total area. Similar to before, we look at the remaining sections of the square, which can be thought of as 8 other smaller squares, and remove the interiors of those squares. We continue this process to infinity, and then you get a fractal called Sierpinski's Carpet. Once again, we can analyze its dimensionality by taking advantage of its symmetry. Notice that there are 8 smaller squares around the perimeter of the large square, each representing an area of 1/8 of the total. Also note that each of these squares is scaled down by x equal to 1/3 relative to the large scale. Why? Well, because the lengths of their size are 1/3 the length of the larger square. So once again, we can use the formula that the area of the small square is equal to x to the power of d times the total area. That comes out to 1/8 is equal to 1/3 to the power of d, and you can figure out that d is equal to 1.893. So once again, we end up with some kind of dimension in between a one-dimensional and two-dimensional object. Notice that this time we're much closer to a two-dimensional object. And you can kind of see that since we were taking away less area from the square in each iteration. There seems to be a little more left over as compared to Sierpinski's triangle. Regardless, it's still very strange. It is even possible to carry on this operation in 3D with a fractal object called Menger's Cube. In this case, you would remove the cube in the middle of the volume and continue this process with the other scaled down cubes. Ultimately, the dimensionality of this object is 2.727. So it has more dimensionality than a two-dimensional object, but it's not quite three-dimensional either. Finally, let's look at one more example called the Koch Snowflake. We can build up this shape by adding two sides of an equilateral triangle to each line segment at each step of the process, repeated infinitely many times. The fractal part of this image is along the edges. We can take one such edge to see how it is built up at each stage. Notice that this is being constructed by adding line segments, which are one-dimensional components, at each step of the way. Yet, the dimension of the fractal object turns out to be 1.26, which is close to a one-dimensional object, but with some part of it in a little bit of area. Somehow, by adding one-dimensional line segments, they've become crumpled up into a higher dimension. Additionally, if you look at each stage, you'll see that each line segment is actually augmented to include an extra 1/3 length. So at each stage, the length of each part of the fractal grows by 4/3 in length, which means that the total length of the perimeter grows by a factor of 4/3. This pattern continues toward infinity. So 4/3 times 4/3 times 4/3 times 4/3 and so on. But that means that the total length of the crumpled perimeter of the snowflake becomes infinitely long. It can also be found that the interior area that is enclosed by the snowflake is equal to 1.6 times the area of the original triangle in the first step. If we assume the original triangle had an area of 1, then paradoxically, an infinitely long perimeter surrounds a finite area of 1.6. Definitely very strange, and thank you for watching, and remember, oddly real, really interesting.